Welcome back to the Deep Dive. Today, we are cracking open a document that is, well, it's dense, it's technical, but it's absolutely essential. It's called The Definitive Guide to Generative AI 2025.
Yeah, this is one of those foundational reads.
Absolutely. If you want to get past just clicking buttons on a website and really understand the machinery behind all this text and image and code generation, this is your deep dive. So the source material is really pointing to this huge shift, right? We're moving away from that old era of software.
The rigid deterministic stuff, all rule-based.
Exactly. And we're moving into this new world defined by probabilistic learned systems. The outputs can feel like magic, but they're all underpinned by these rigorous observable systems.
And that's really the core mission today, isn't it? We want to get you, the listener, past just using a public API.
Right.
I mean, if you want to build or fine-tune or deploy these things reliably, you have to understand the mechanics, the training, the alignment, the real technical guts of it.
So when we start throwing around terms like backpropagation or latent diffusion, you won't just know what they are.
You'll know why there were such huge breakthroughs. The goal here is to make this whole thing feel less overwhelming.
And the immediate hook, really, is that this magic, this active creation, is all just high-level mathematics operating in these incredible high-dimensional spaces. So let's start there. The invisible engine. Okay, so to unpack this, we're really talking about geometry. We have to start with linear algebra and these latent spaces.
Linear algebra is just the language of modern AI, full stop. Every single thing, a word, a pixel, anything, it gets translated into a numerical format.
A tensor.
A tensor, which is just a fancy name for a multidimensional array. All that talk about massive matrix multiplication, that's just tensors interacting with each other.
And the critical bridge, the thing that lets a computer process something abstract like the word cat, is the embedding vector.
That's right. It's a dense, continuous numerical representation of that word. But the important part isn't just turning words into numbers.
It's the geometry, the relationship between the numbers.
That's it. The geometric relationship captures the semantic meaning.
Can you give us that classic example, the one everyone always goes back to?
Of course. The king, man, woman example. It's the one to hold on to. You take the vector that represents the word king.
Okay.
Then you do some simple vector arithmetic. You subtract the vector for man, and then you add the vector for woman.
And the resulting vector lands closest to
the embedding for queen. The model learned that this simple linear translation captures a concept like royalty or gender. It's that geometry that allows for complex analogical reasoning.
Okay, so that sets up the structure. Now let's get to the engine that drives the learning. Calculus. Training a model with billions of parameters, that's just an optimization problem, right? We're just trying to minimize error.
Precisely. And that optimization is all driven by the gradient. Just think of your loss function as a hilly landscape. The gradient is a vector that points in the direction of steepest ascent.
The fastest way up the hill.
Right. And since we want to minimize error, we just move in the opposite direction. That whole process is called gradient descent.
That makes sense for a simple function, but how on earth do you calculate that gradient efficiently across hundreds of layers with billions of parameters?
That is the absolute genius of backpropagation. It's an algorithm that just uses the chain rule from calculus, but recursively.
So it works backwards from the end.
Exactly. It starts at the final output error and goes all the way back through the network, calculating how much each individual weight and bias contributed to that final mistake. It's like assigning credit or blame to every single neuron.
And without it.
The process would be prohibitively slow. It just wouldn't work at scale. Backpropagation is what makes deep learning possible.
So we have linear algebra for the structure, calculus for the learning. The final piece of the puzzle is probability. This explains why the output is never quite the same twice.
Right. Generative models aren't trying to just memorize the training data. They're trying to model the underlying data distribution. Call it OTIX, $5. They're learning the likelihood of things.
So for a language model, its main job is what? Maximum likelihood estimation?
MLE. It's constantly just calculating the probability of the next word or token, given all the ones that came before it. That probability distribution is why you get slight variations every time you hit generate.
And how does the model know if its probability guesses are any good?
We measure the difference with something called cross-entropy loss. It's the standard for this kind of thing. It basically quantifies surprise.
Surprise.
Yeah, if the model predicts a word with a 90% confidence, but the real word in the data was something completely different, the loss or the surprise is very high. The entire goal of training is just to minimize that surprise.
Okay, so those mathematical tools, they enabled the architectures we have today.
Absolutely. The capabilities you're seeing now in 2025 are the result of this evolution, a sort of architectural family tree.
Let's start with maybe the oldest sibling in that family. Variational autoencoders, or VAEs.
VAEs were a huge step. A normal autoencoder would just compress an image into one fixed hidden vector, but a VAE, it maps that input to a whole distribution.
Defined by a mean and a variance.
Right, a mean, mu, and a variance, sigma. So when you generate a new image, you just sample from this learned distribution. The key technical bit to make it all work, though, is the reparameterization trick, which you need to get the gradient to flow back through that random sampling step.
VAEs had that great, smooth, latent space. You could morph between outputs beautifully, but they had one big problem.
The blurriness, the output images always looked a bit fuzzy.
Yeah.
And that blurriness happens because under the hood, VAEs are trying to optimize for pixel level accuracy, and that's the exact problem that the next big family solved. Generative adversarial networks.
Doyens,
They just decided to ditch that pixel optimization and use a game instead.
a minimax game to be specific, between two competing networks.
The generator and the discriminator. Exactly. The generator is the forger, trying to make stuff so realistic it fools the discriminator. And the discriminator is like the art critic, trying to tell the real data apart from the fakes. This constant battle, this adversarial dynamic, is what pushed the outputs to become incredibly sharp.
But the trade-off was stability. You always hear about how hard GANs are to train.
Oh, they are notoriously unstable, and the main reason is something called mode collapse.
Mode collapse.
Yeah, if the generator finds one specific output, let's say a picture of one particular cat that always fools the discriminator, it gets rewarded and it just stops learning. It'll just produce that one cat over and over, ignoring all the other types of cats in the training data. It collapses on one mode.
So, if VAEs are blurry and GANs have mode collapse, where did researchers go to get both the high fidelity and the diversity? And this is where it gets really interesting, right? Diffusion models.
Yeah, drawing inspiration from thermodynamics of all places.
Right.
And they are just beautiful in their simplicity. The whole thing is two halves. You have the forward process, where you slowly, meticulously add noise to an image over thousands of steps until it's just pure static.
Okay, so you destroy the data.
And then you have the reverse process, where you train a network, usually a UNet, to predict and subtract that noise step by step to get back to the clean image.
That sounds incredibly slow. Thousands of steps for every single image. What was the innovation that made this usable for everyone, like with stable diffusion?
That was the latent diffusion model, or LDM architecture. Doing that denoising process in full pixel space was just too slow, too expensive.
So he didn't.
He didn't. LDMs use a VAE first to compress the big image into a much, much smaller latent space. The whole diffusion process happens in that compressed space.
So you're saving orders of magnitude in computation.
Exactly. That's what democratized high-quality image generation.
But none of this, not VAEs, not GANs, not diffusion, would work at today's scale without the transformer. That's the universal architecture that really changed the game.
The transformer just solved the fundamental bottleneck of older models like RNNs, which had to process a sentence one word at a time. The core innovation is self-attention.
Self-attention. And for every word, it calculates 3 learned vectors.
3 vectors. Query, which is Q, key, which is K, and value V.
And the magic is how those 3 interact.
Yes. The model computes these attention scores by multiplying the query and key vectors. That calculation basically determines how much attention to pay to every other word in the entire sequence.
So it can look at the whole sentence at once.
In parallel. And it can dynamically attend to relevant words no matter how far apart they are. That parallelization and the ability to capture long-range dependencies. That's why the transformer is the backbone of every modern LLM.
That power brings us right to the modern industrial process, the LLM factory. Building these models is basically a 3-phase pipeline now. Let's start with phase 1, pre-training.
This is the massive resource sink. This is where the model gets its world knowledge by just consuming trillions of tokens of text.
And a key detail from the source is the focus on data quality, specifically deduplication.
Absolutely essential. You have to remove duplicate documents. If you don't, the model just wastes its time memorizing things instead of learning to generalize concepts.
And what about the size of the model versus the size of the data? That's all dictated by the scaling laws, isn't it?
Yes, specifically the chinchilla scaling laws. At first, everyone just focused on making models bigger and bigger, but chinchilla showed that's inefficient. For optimal performance, you have to scale model size and data size proportionally.
So a smaller model on more data can actually be better.
Often, yes. Better than a massive model that's been undertrained.
Okay, so once you've done this massive pre-training, you have a brilliant but kind of passive document completer. To turn it into a useful assistant, you move to phase 2,
Yeah.
supervised fine-tuning, or SFT.
And this is where the engineering pragmatism really comes in. Fine-tuning a whole 70 billion parameter model for every single task is just prohibitively expensive.
Which is why we have PEFT, parameter efficient fine-tuning.
Exactly. And the most critical technique there is LoRa, or low-rank adaptation.
And what's the practical impact of using LoRa?
Well, LoRa lets you freeze all the massive original weights of the model. You only have to train these two tiny low-rank matrices, A and B, alongside them. It's like adding efficient little sticky notes instead of repainting the entire building.
And that reduces the trainable parameters by.
Up to 99.9%. The breakthrough is democratization. It makes custom fine-tuning affordable for basically everyone.
Okay, now to the critical step, phase 3, alignment. This is making sure the model is helpful, honest, and harmless.
And the gold standard for this has been RLHF, reinforcement learning from human feedback.
Which is a pretty complex process.
It is. First, you have human reviewers rank model responses. That's your preference data. Second, you use that data to train a separate reward model like an AI coach that learns to predict what a human would prefer.
And then finally,
You use reinforcement learning to optimize the main LLM to maximize the score from that reward model.
but that RL part, using PPO, it's notoriously unstable, right? So what's the big emerging alternative?
That would be DPO, or direct preference optimization. DPO is so much simpler. It gets rid of the separate reward model and the unstable RL loop entirely. It just optimizes the LLM directly from the preference data. It's more stable and much easier to implement.
So once we have this aligned LLM, we need to use it in the real world. But a huge problem is the knowledge cutoff. It doesn't know about last week's news or a company's private data. How do you solve that?
You solve it with retrieval augmented generation, or RAG. The model isn't asked to just remember things. Instead, it queries an external vector database.
Ah, so it retrieves relevant context.
Exactly. It retrieves chunks from up-to-date documents, and then it injects that context directly into its prompt before it even tries to generate an answer. It keeps the model grounded, in fact.
And the sources really stress that good RAG is about smart engineering, not just search. What are the key details there?
Two things are critical. First is chunking. Just splitting documents by a fixed length is bad. The best pipelines use semantic chunking, where you split the text based on meaningful content boundaries.
Right, like at the end of a paragraph.
Precisely. And second is re-ranking. Your first database search might return, say, 50 decent chunks. A separate, slower, but more accurate cross-encoder model then acts as a quality filter. It re-ranks those 50 down to the top 5 most relevant chunks. That ensures the LLM only sees high-quality context.
So RAG helps the LLM answer better. Now we shift from passive answering to active problem solving, getting the LLM to act. And that brings us to AI agents.
Right. And you start by guiding the LLM's internal thinking with better prompting. The simplest one is chain of thought, or Cote.
You just tell it to think step by step.
That's it. And because transformers generate tokens one after another, this forces it to output its reasoning steps first, which effectively gives it more computation time to work through the problem before giving a final answer.
And the foundational architecture for agents that can actually use tools is REACT.
REACT, which stands for reasoning and acting. It just codifies this continuous loop that defines what an agent does. First, the thought, where it makes a plan. Second, the action, where it uses a tool, like an API. And third, the observation, where it sees the result and starts the loop over.
This move to agents means the whole system gets a lot more complex than just the LLM itself.
Oh yeah. You need at least 4 key modules now. The big ones are memory and planning. For long-term memory, agents use a vector database to store past interactions and knowledge.
And planning.
Planning is about decomposition, breaking a big goal into smaller tasks. And reflection, which is the ability to look at a failure and critique its own plan.
And we're even seeing multi-agent systems now.
We are. The source talks about things like a hierarchical structure, a manager agent giving tasks to worker agent, or and this is really interesting, joint collaboration.
Where you have agents with different personas.
Exactly. You might have an optimist agent and a pessimist agent that debate a problem to reach a more balanced conclusion.
That brings us to the final frontier, multimodality, handling text, images, audio, all at once.
And the key enabler for this, mathematically, is CLIP, contrastive language image pre-training.
Right.
CLIP trains two parallel encoders, one for text, one for images, on just tons of paired data. And the goal is really elegant. It learns to embed the correct image-text pairs close together in this shared latent space while pushing incorrect pairs far apart.
So it mathematically aligns the world of language with the world of vision. What does that mean for generative models?
It means CLIP acts as the mathematical guidance system. When you type a prompt into Stable Diffusion, CLIP is what compares the image being generated to your text and provides the gradient to steer the diffusion process toward a match.
Okay, what about audio? That has unique challenges because of the high sampling rate. How do models like audio LDM solve that?
They use a really clever workaround. They basically turn the audio problem into an image problem. They convert the raw audio into a Mel spectrogram, which is a visual representation of the audio's frequencies. They then do latent diffusion on that image. Finally, they use a neural network called a vocoder to turn the generated spectrogram back into a high-fidelity audio waveform.
And for video, the final piece, it seems like it's all about solving one thing, temporal consistency.
That is the whole ballgame. Video is just making a sequence of images that don't flicker or have objects randomly change, so you have to inflate the 2D image models into 3D and add powerful temporal attention layers so the model can look back at previous frames to keep things stable.
So we've tracked this journey from math through architectures to these industrialized pipelines and agents. The source makes one final point very clear. Generative AI is moving from the model era to the system era.
The focus is completely shifting to orchestration. The next breakthrough isn't just a bigger model. It's how skillfully you can orchestrate all these components, the LoRa, the RAG, the agents, into a reliable and effective workflow.
And for you, the listener who wants mastery, the roadmap is clear. You need both. The theoretical rigor to understand the math and the architectures, and the engineering pragmatism to actually build these RHE pipelines and React agents.
And as these systems become more autonomous, more orchestrated, it raises a huge question about liability, about risk. The risk shifts from a simple error to a systemic failure. And one of the most surprising countermeasures we're now seeing is vendors offering legal indemnification.
So,
Yeah.
if the model spits out something copyrighted and the user gets sued, the vendor will cover the legal costs.
Exactly. And that is a massive shift in market risk. It leaves you with this really provocative question to think about. If the enterprise vendor is willing to take the financial liability for the AI's output, who is ultimately responsible for what a model creates? That relationship between creation, autonomy, and legal risk, that is the next frontier you'll have to navigate.